Welcome back, everybody. We're on notes number 2 today, and we're going to review transformations. There is a handout you can print. It's posted on Canvas, so if you don't want to have to write everything and if you have access to a printer, you could go ahead and do that. What you see in the white squares here is on the handout, and then I'm going to give you some examples off to the side. So transformations are ways to change how a graph looks by either shifting it up or down or left or right, or stretching it vertically or horizontally, or shrinking it, or reflecting it. So the first section we see here has to do with shifting up or down, left or right, and that is also called translating. So these are translations, and let me give you an example. So let's say our parent graph is f of x equals x squared. If we change it to f of x equals x plus 2 squared, that's going to shift it left 2. Now when you see the plus 2 there, you would probably intuitively assume that it was going to go right, but it's actually the number you're subtracting from x that tells you which way you're going. And if you see x plus 2, you're subtracting negative 2, and so you're going 2 to the left. Okay, if you have something like f of x equals x squared and you change it to f of x equals, let's say, x minus 1 squared, that's going to translate it 1 unit to the right. What we subtracted from x was positive 1, so that moves it right 1. Now if you add and subtract numbers to f of x, but instead of doing it inside the squaring, if you do it outside the squaring, or as I sometimes say, outside the function, such as if you change f of x equals x squared to f of x equals x squared plus 9, that's going to shift the whole graph up 9 units. And if you changed it to f of x equals x squared minus 5, that would shift the whole graph down 5 units. So that's pretty intuitive. Plus 9 was up 9, minus 5 is down 5. The 9 and the 5 outside the squaring, not inside the squaring. In the next section, we look at reflections, and reflections occur when you multiply your function by a negative sign, or multiply it by a negative 1. So let's say once again we're starting with f of x equals x squared, and if we change it to f of x equals the opposite of x squared, what that's going to do is it's going to take all the values and multiply them by negative 1, and so that's going to reflect the graph in the x-axis. It's going to flip the whole thing upside down. If you took your graph f of x equals x squared and you changed it to f of x equals the opposite of x squared, so this time instead of multiplying the outside by a negative, we multiplied the inside by a negative, what we're going to notice is every time the change is on the inside, it's a horizontal change, and every time the change is on the outside, it's a vertical change. So if we look back, this change was on the outside, it was a vertical change. This change was on the outside, it was a vertical change. This change was on the outside, it was also a vertical change because it flipped over vertically. And every time you have a change happening inside the squaring, it's a horizontal change. So moving left is horizontal, moving right is horizontal, and multiplying the x by a negative is also going to give us a horizontal change. That's going to be a reflection across the y-axis. So it's reflecting sideways, you could say. Now it just so happens for this particular function that I've chosen as my example, it's not going to look any different if you look at f of x equals x squared, which would look like this, or f of x equals the opposite of x quantity squared, where you flip it across the y-axis. It's going to look the same. Okay, it was originally an even function. Reflect it across the y-axis, you still have that same function. And you could tell that if you wanted to simplify that, when you square the negative, you're going to get a positive. But there are some graphs which, of course, would look different if you reflect them in the y-axis. For example, if you had a square root graph and you reflected it across the y-axis, it would look different. Okay, and the third section is labeled dilation. That's not a word we used really in pre-calc. We used the word stretches and shrinks. Here we're seeing stretches and compressions, so it means the same thing, just a different term. Once again, if you do something to the outside of the function, it's a vertical change. So if you multiply the outside of the function by a number a, and if the absolute value of a is greater than 1, so if a is 2 or 3 or 4 or -2 or -3 or -4, it's going to be stretched vertically. So if I took my original f of x equals x squared and I changed it to f of x equals 2x squared, it's going to be stretched vertically twice as tall. Vertical stretch times 2. Now if that number a that we're multiplying on the outside of the function has an absolute value between 0 and 1, like 1/2, 1/3, -1/2, -1/3, then the graph is going to be 1/2 as tall or 1/3 as tall, so it's going to be a vertical shrink. So here's my example, f of x equals 1/2 x squared, vertical shrink times 2, meaning twice as short or half as tall. Next, you'll notice that we're multiplying the value of x inside the function by some number b. So it's an inside change, so that's going to be a horizontal change. And if that number b is greater than 1, 2, 3, 4, etc., 1.5, 1.1, something greater than 1, then it's going to be a horizontal shrink. Okay, that is counterintuitive. You might expect it to be a horizontal stretch for a larger number, but it's actually a horizontal shrink for a larger number. I'm going to switch to a different example for this, and you might remember this from pre-calc if you had me. Suppose my function was f of x equals the sine of x, and I change it to f of x equals the sine of 2x. So the 2 is being multiplied inside the sine function. Do you remember me talking about that being a roller coaster that is 2 times the fun? So if you picture your sine graph, it looks like this. That looks pretty fun. This is 2 pi, 1 complete cycle. But if you horizontally shrink it, then in the same width, you're going to have twice as many curves. And that roller coaster is going to be 2 times the fun. That's the way I like to remember that horizontal shrinks use a number greater than 1, and then that means that horizontal stretches are going to use a number between 0 and 1. For example, if you took f of x equals sine of x and you changed it to f of x equals the sine of 1/2 x, that roller coaster is only going to be 1/2 the fun because it's stretched horizontally, so in a width of 2 pi, you're only going to see half of that curve. Okay, hopefully you recall, with just this small amount of reminding, those transformations that we've learned in the past. And what we're going to do next is look at some examples. So we also have a handout for this practice problem as well as the next practice problem. And what you see here, number 1 says the graph of f is given. So it's a red piecewise function. We're not given the equation, and that's totally fine. We're just given the graph. All we need to do is draw the graphs that are described in parts A, B, C, and D. So each time I've shown you the original f of x in red, so you can easily reference it as you're drawing the transformed graph. Okay, part A. We want to draw y equals f of x plus 4. So what have we done to f of x? We've added 4 inside the function. Remember, doing something inside is a horizontal change, and it's counterintuitive. Adding 4 is actually moving it left 4. So what I'm going to do is take some of the key points that I see in my graph and shift them to the left 4. So the point that's right here, I'm going to shift it left 4. The point that's right here, left 4. The point that's right here, left 4. And the point that's right here, I didn't really allow myself enough room, but let's pretend that's left 4. So then we sketch that. It looks the same size and shape as the original. It was just shifted over. If it has the same size and shape, it's called an isometry. Iso means same, metry for measure. So if you just shift, you have an isometry. If you just reflect, you have an isometry. If you stretch or shrink, you don't, because you're going to change the shape. Okay, let's look at part B. Notice we're adding 4 just like we did in part A, except the plus 4 is outside of f of x. So that's going to be a vertical shift. So we're going up 4 units. So let's just take the key points and shift them up 4 as well as we can, given the space we have. Something like that, and that. And then we'll connect those key points. And there we have our transformed graph. Part C, we're multiplying the function by 2, and the 2 is on the outside, so that's a vertical change. And that 2 is greater than 1, so it's a vertical stretch. It's going to be twice as tall. So what we do if something is twice as tall is we double the y coordinates of the points. We don't change the x coordinates, but we double the y coordinates. This point down here has a y coordinate of 0, and when you double that, it still has a y coordinate of 0. So if a point is on the x-axis and you stretch it, it's still going to be on the x-axis. This point here has a height of 4. I need to double that and get a height of 8. Something like that. This point has a height of 1, double that and we have a height of 2. And this point has a height of 2, double that and we have a height of 4. Now let's connect those points. Imagine that that was nice and straight there. Okay, so it doesn't look any wider. We didn't change the width. It just looks taller. Now part D involves 3 transformations. So what I'm going to do is do them one at a time, kind of working my way from f of x and then what's nearest to it and working my way out, thinking about order of operations. So f of x gets multiplied by 1/2. I'm going to do this part in gray. It's kind of a dotted gray. That means it's going to be 1/2 as tall. So take the key points and take half of their heights, half of their y coordinates, and then connect them. Now the negative means we're going to reflect it across the x-axis. It's a vertical change, so a vertical reflection. Any point that's already on the x-axis is going to stay there. And then you can connect those key points. And then finally, for our answer, I'll do this one in red. We're going to shift the whole thing up 3. So take those key points and shift them up 3 units. And then connect. Okay, there we go. One more example. Here we have a trigonometric example. We're looking at the graph of f of x equals sine x. So there's our roller coaster. And we're going to draw the transformed functions. We have our sine graph each time for reference. So for part A, we have a number subtracted from x inside the function, so we're shifting to the right. So we're going to go right pi over 2. Remember, pi over 2 radians is equivalent to 90 degrees. Just kind of get that trig flowing back through your brain again. So let's shift everything right pi over 2. So this point, which was at x equals 0, is going to be right here, and this point is going to be here, this point is going to be here, this point is going to be here, and so on. It doesn't tell us where we have to start and where we have to stop, so I suppose we could just do something like this. Call it good. Okay, part B, we're subtracting 1 outside of f of x, so that's going to be a vertical shift, down 1. Okay, so the point that was at a height of 0 is now at -1, and the point that was at a height of 1 is now at 0, and so on and so forth. The point that was at a height of -1 is now at a height of -2, and we can go ahead and connect those key points. Let's look at part C. We're multiplying by 1/2, and the 1/2 is outside of f of x, so that's a vertical shrink. It's going to be half as tall. So we take the y coordinates of the points and we cut them in half. 0 cut in half is still 0. 1 cut in half is 1/2. -1 cut in half is -1/2. The graph's width did not change, it just got shorter. And for part D, we have the 1/2 inside the function. So that roller coaster is going to be 1/2 the fun. That means a horizontal stretch by a factor of 2, 2 times wider. So let's take our points and double their x coordinates. Doubling 0, you're still at 0. Doubling pi over 2, now you're at pi. Doubling pi, now you're at 2 pi. I don't really have enough space to draw the entire curve again, so I'm just going to draw the half of it that I can fit. And if I had more room, I would be drawing the other half over there. Okay, for your assignment, I would like you to do this page out of the book and these numbers, and I've attached a PDF to Canvas so that you can see the book page, and also I've attached the answers. Thank you, everybody. Let me know if you have any questions.